video camera? Great. So our first speaker of the afternoon is the big Shende, and he'll be telling us about Skeins on branes.
Yeah. Well, thanks for the invitation. It's a pleasure to be here in Miami and speaking in honor of Kenji's 60th birthday. 60th birthday. So I think you're supposed to tell some kind of funny story. I haven't been around so long, so I don't have so many funny stories. But the last time I had to speak and Kenji was in the audience was at IHS, and it was right after lunch. And at the end of lunch, Kenji told me that he had eaten too much lunch and he would sleep in my talk. Anyway, so hopefully maybe not too much lunch this time. Okay. So let me begin by explaining which problem I'm trying to solve. This goes back to the 80s, when people, Jones and then after him, about 8 more people, discovered some new knot invariants. And I'm going to formulate the result in a way that's suitable for what I'll use, but it's what they do. So if you take the free abelian group generated over this ring by embedded configurations of circles in S3. And if you take this modulo, the following three, well, first of all, isotopy, and in addition, the following 3 relations. I should say they're framed circles. So you can, in these pictures I draw, so framing means you fix a tangent vector normal along the knot, and in the pictures I draw I take black-white framing, so the normal vector comes out. And so these 2 pictures have different framing, and this rule says you're allowed to change the framing, but it costs you an A. And then this next rule says you're allowed to change a crossing, but it costs you an additional knot and a Z. And the last rule says you're allowed to take away an unknot, but it costs you a Z and an A minus B. Okay, so these are these are what are called the Skeins relations. And this quotient is called the Skeins module. And the theorem that these people proved and everyone was excited about back in the day is that this item, which has this huge amount of generators and these 3 relations, is in fact just the original invariant. Now the way that people wrote it back then is they would say, so maybe the corollary of this theorem is you can define a knot invariant by saying that I take the class of K in this, I take my knot K, I take its class in this quotient, and I compare it to the class of the empty knot. And whatever, well, it's the thing is one-dimensional, so it'll be some multiple of this, and that multiple is called the Homfley-BT polynomial. Okay, so that's from back in the 80s. And also that, but one difference between this knot invariant and the ones that came before it is that no one knew what it meant. Didn't have a topological explanation. The Alexander polynomial is something about monodromy of the cover, but this one is a mystery. So then, a few years later, Witten he gave some kind of explanation. And his explanation, I'll write it as a formula, which is this, I shouldn't use this because I'm using this for the class in the Skeins module. This knot invariant is equal to the following quotient. You take an integral over all connections, and you integrate Chern-Simons functional, and you also put in the integral the holonomy around the knot of your connection, and you divide this by just the integral of the Chern-Simons functional. Now, for physicists, this was a great explanation, but for mathematicians, not so great, because this integral, no one knows how to define it. After this, Witten said something else. He said that, so maybe 10 years later.
So what is A and Z for this moment?
Yes, let me see it. So A, so in here is supposed to be a Q, which I didn't write, but let me, let me first write A in terms of Q. Okay, so A is supposed to be Q to the n over 2, and Z is Q to the 1/2 minus Q to the negative 1/2. And what is Q? Q in here is some like kth root of unity.
So this is SU2 Chern-Simons theory?
N.
SU.
And then Witten told us something else. He said afterwards, so I'll just say it out loud. He said that Chern-Simons theory on M is supposed to come from string theory, open string theory, and the cotangent bundle of M. Now what this means is a bit of a mystery. So maybe I'll say why Witten believed it. So he wrote, so string theory can be written as a certain kind of field theory, and you can write the action for these fields. And in some degenerate limit, the action for the open string, it looks like the Chern-Simons functional. That's what happens when the open string sort of collapses to the brane it's supposed to end on. And so that's a little bit confusing. But from this, Aguri and Vafa, they somehow managed to extract a prediction. And the way they did this, so here is some manifold M, maybe S3, and you take a knot on there, you take the conormal bundle to the knot, and you push it off a little bit. So this is a picture taking place inside T star S3. Here we have a copy of the conormal bundle of the knot pushed off a little bit. And once you do that, you can study open strings stretching from the conormal bundle of the knot to M. So let's study open string. And the way Aguri and Vafa interpreted this Witten statement is that the correction to the open string, maybe the correction of Chern-Simons on M and N star K given by this open string is this K. So that's some form of this Aguri-Vafa prediction. And moreover, they said that if M is S3, then you can shrink the S3 down to a point, pass through the conifold transition, and just count curves ending on N star K in the resolved conifold. So that's the
So what do you mean by correction to CS?
So if you believe Witten, open strings somehow just on one brane recovers Chern-Simons on that brane. The statement is you have two branes, and you have an open string so that open strings can stretch between them, then the correction to that, then somehow each somehow of these instantons will correct the basic Chern-Simons, in fact, by k here and k there. Like it's k times k. So this is just some sort of motivation for what I'm going to say now, but I put it in part to be clear how close I'm going to stay to the physics in what is hopefully now precise mathematics.
So these are Boolean work from the other side of the work chain transition.
I mean, first they said this, and then they go through the transition. And you know, first you do this, and then you take this S3, collapse it to a point, resolve it, and then you only have this one left. So the reason why this Aguirre-Vafa proposal is better it's better in a sense than this Chern-Simons business. The reason it's better is that here, you know, counting holomorphic curves, or in other words, studying just the instantons of the topological string theory, is something we know how to do. Whereas this integral we do not. For instance, if there was no branes at all, the analogous thing would be computing usual Gromov-Witten theory. This thing, you should think, is making some prediction about an open Gromov-Witten theory. But there's a problem. So the problem that remains even after coming here is that open Gromov-Witten theory is hard to define invariantly. But I want to emphasize this difficulty is not the impossible difficulty of this integral dA. So the reason why open Gromov-Witten theory is hard to, maybe to explain why open Gromov-Witten theory is hard to define, let me remind you how to define closed Gromov-Witten theory. Reminder. Closed Gromov-Witten. And I'm going to take the simplest possible case. And when I say simplest, I mean where you can expect the moduli space to be zero dimensional, which is in Calabi-Yau 3-4. So the idea is you choose a perturbation of the holomorphic curve equation. And after you do this, then your belief about the moduli space being zero dimensional becomes the truth, and you wind up with some, you know, this is the moduli space. And you can just count. Of course, you have to choose that perturbation, and what you should show to convince yourself you did something reasonable is that the answer didn't depend on the perturbation. So maybe I take some other perturbation, and now you might worry that maybe there's going to be a different number. This would be a problem. But the reason this problem doesn't happen is you connect these perturbations by some path, and you ask about holomorphic curves, which return holomorphic with respect to any perturbation along this path, and you study that. And the claim is that you have to get a cavoidism. In other words, the total space of that moduli should be smooth. And roughly speaking, the reason for that, you know, for it to be literally true, you have to say a lot of stuff, but roughly speaking, the reason for that is that this holomorphic curve theory, you can ask, what could go wrong with the holomorphic curve equation? And Gromov explained that the only degenerations are when energy concentrates at some point, and that's a codimension 2 phenomenon. So you never see it in one. Okay, so that's the basic reason why Gromov theory exists. So what about the closed case, or the open case? In the open case, the basic problem is that now your curves have boundary, and you can have boundary degenerations, and as you all know, that's a codimension 1 phenomenon. Boundary generations. This is the codimension 1 phenomenon. So, in the open case, now your moduli spaces themselves have boundary. And if you were to count, if you were to just count, you would no longer get an invariant number, and then you're out of luck. So the first task is to explain how to nevertheless count the curves in an invariant way. And there have been many approaches to this over the years. Kenji is responsible for some of them. Some approach by Welchanger. So let me explain what is the enemy. So I mean, what causes this problem? So one source of this problem. So here's a Lagrangian. And you might have some holomorphic curve, looks like this. One source of this problem is the boundary kin pitch of this curve. So you could have this. Not boundary pinch, sorry, this. And this would be a boundary of that moduli space in one Slepper family. And there's a similar problem. So instead of the boundary pinching in this way, you can also have the boundary, the circle going to radius 0. Okay, that's the other problem. So let me call this 1, this one 2. And I want to draw another picture, this time just from the point of view of the Lagrangian. So from the point of view of the Lagrangian. So from the point of view of the Lagrangian, this problem 1, it looks like this. I don't know if. So maybe originally the boundary of this curve, it looked something like this. That's the circle in the Lagrangian. And then, as it degenerates, now, not like this. It is better to draw it this way. As it degenerates, let's try to stroke like that. And problem 2 from the point of view of the Lagrangian, this is 2, as well, the circle, it goes to nothing. And I hope you already, well, maybe not quite yet. So let me tell you the solution. As far as I know, this is a kind of new way of solving this problem. And the basic observation is at this singular moment, there's another curve with the same image. Okay, the way I've drawn it you're supposed to think about this broken curve as an embedding of a curve that looks exactly like this. But that picture, you could also read it a different way. You could read it as the immersion of a disconnected curve. That's a okay way to read this. And this second picture, again, you're supposed to think about it as an embedding of a curve with a real node, and it's a little bit hard to think about what a real node is when the node is on the Lagrangian. But you can also think about it as a map from a sphere. So the use of that is that as you're, in addition to this bad family, which ends in the middle of the cuboidism, it ends in a way that looks like this or like this, there's a second family. And that second family is this map from the immersion. And when you deform this immersion, it deforms in a one-parameter family. It has no reason to stop. So let me draw the deformations of this map from the immersion from the point of view of the Lagrangian. So from the point of view of the Lagrangian, still this central one has two circles. They intersect at some point. In fact, let me not even draw the whole circle. I'll just draw this piece of it. But just forget about holomorphic curves for the moment. If you have an immersion in 3 space of a curve, and it has a singular point, well, there's 2 ways to perturb that. You can perturb it this way, or you can perturb it that way. So there's a one-parameter family of curves as you perturb this one. It looks like this. And you can think about this immersion of a sphere and just perturb it. And that one-parameter family is a bit harder to draw. So now here's the Lagrangian. Lagrangian. Here there's a sphere that has coincidentally met it at one point. You perturb a little bit, it's off completely. You perturb a little bit. Maybe I'll just draw it underneath. It misses it in a different way. So maybe there's not a solution yet. I've just told you this other family. Something to observe. If you compute the topological Euler characteristic of the source of this other family, it is 1 less than of this original one. Okay, good. So now the solution to the problem is that we count curves by the class of their boundary, by their boundaries. As elements in this Skeins model. So let me first of all say that this is what the physicists were telling you to do all along. And the sense in which that's true is that the physicists said that this holomorphic curve had some correction, it's an instanton correction of the Chern-Simons theory. And what is the space of corrections of the Chern-Simons theory? Well, it's defects in the Chern-Simons theory. It's known what that is. And the only thing, the most natural thing which specializes the defects in Chern-Simons of SUN for all n is this Skeins module. So that's why you should have believed before I started that you should count curves by their boundary. And the reason the reason it solves this problem is, well, let's consider this problematic family where you have a curve which degenerates to this kind of curve. So at the same time, you have a less problematic family where you have a curve, you have two curves, which one map from them looks like this, then at some moment their images had met, and then the map from them looks like that. So, like before, before the reason for the invariance of closed Gromov-Witten theories, there was some cuboidism of moduli. And now there's also cuboidism of moduli, except one piece of the cuboidism ends. But nevertheless, whenever I see this ending piece, I also see this piece. So the whole thing is invariant, the situation is invariant modulo the boundary of this whole setup. Okay, so we always see the problem together with this. We always see this problem together with this this other thing.
Is that particularly 3 dimensions?
Yes.
So what is the thing?
So there's this where the curve, this one or this one?
The bottom one, right?
The bottom one is the one parameter deformation of the immersion of 2 at one point.
But you meant the boundary of the whole 2 parameter.
And it's one parameter. So I explain what this picture means more precisely later on. So when you choose a perturbation, so I'll say it now and I'll say it more precisely later. When you choose a perturbation, you should choose perturbations for each one of your moduli, for each one of your holomorphic curve problems all at once. And the important thing is going to be to ensure that you choose them compatibly.
They all are going to be 1 parameter perturbations.
So at this moment in time when I define my invariance, I choose a perturbation in every genus, it's okay to do it for 1 degree at a time, but for every genus.
But it's still 1 parameter for every genus.
Well, here it's 0 parameters, and here are 0 parameters, and to connect them I use 1 parameter.
Well, it's 1 parameter.
1 parameter. Because I'm just trying to prove invariance. So okay, so what is the boundary of this thing? Well, if we weren't paying attention to the curves themselves, the boundary of this thing would be 2 minus 1, which is 1, and I'd be trying to count modulo 1. That's not a good idea. But what the boundary of it actually is, well, if I look in some small neighborhood of this node, one piece of the boundary looks like this, and the other piece of the boundary looks like this, minus this. And as I told you, this one has Euler characteristic 1 more, 1 less than this one. So to keep track of that, I write C. So modulo this equation, the count of these curves is invariant. This side equals that side. So that resolved one of the problems. And you've seen that equation. So resolving the other problem, problem 2. Well, if I try and resolve it just in the same way, now I'm going to see this family. So I have this is the problem family, and then the not a problem family looks like this. This is a sphere, not a theta. And now if I tried to count by their boundaries, well, I would get you know, the boundary of this right now, it looks like circle plus 0, because there's no boundary of this one. Okay, so I would get the unfortunate equation circle equals 0. And the way to avoid getting that equation is you have to invent some way of distinguishing these two items. And fortunately, this was known to the real algebraic geometers, and more relevant for this was that we're about to say that this whole talk is worked with Tobias Ekholm.
Wait, I don't even understand the difference between those two things.
This circle and this
No,
circle?
no.
One is the boundary, but not.
The two ends of the bottom line.
Right now, there's no difference. That's the problem.
Okay.
I mean, so if I subtract them, I get 0. I get 0 minus 0. And then to make them different, what you do is you introduce somehow bounding forechain on this Lagrangian. So you
Can't
have
see
to
that.
introduce, yeah.
You used to mark it in the pile, it doesn't work.
Oh, I see.
That's why they brought all those boxes.
So you have to introduce this forechain, which I'll describe more explicitly in a bit.
We're making fun of you still.
And so if you do this, then in fact, it's some kind of linking number. And the linking number changes when you cross this thing. Well, I'll explain a bit more later. And the way it changes is like this. And the other thing is that, as I said before, this one has one more Euler characteristic, so you have to write Z here. Okay, so that's the second Skeins relation. That's the third Skeins relation. So now that solves this problem. So this is still just the idea. I'll explain a little bit more later. But let me now state a theorem. Maybe a few. So this conference has gotten me thinking a bit about like what the word theorem means in symplectic geometry. And you know, different people seem to mean different things by it. And as far as I can tell, what theorem means is it's a sort of a theorem when people stop fighting you. So the word theorem is like an invitation to a fight. That's yeah. And since I forgot to say it before, let me say that this is Ekholm. So let me put in parentheses some things maybe I'll explain later, which is that there exists a notion of linking number and a sort of theory of perturbations such that you can write this sum z to the minus Euler characteristic of some map, and this is sort of variables. Okay. And the sum is over this, so I'll have to define this word in a second. So primitive maps from a curve with boundary to Calabi-Yau with Lagrangian. And the term of the sum, the terms of the sum, well, these z, q, and a are just variables. Q may be many variables. This is the relative H2 class of the image of sigma. This is the topological Euler characteristic of sigma. This is the linking number, which I haven't yet explained to you. And this is the boundary of maybe the image of the boundary in the Skeins module of L. And that's what the terms of this are. And what the theorem says is that this is independent independent of the dimensions.
Any assumption of the topology of L?
In some sense, yes. So the place an assumption on the topology of L comes in is in the existence of this 4-chain satisfying certain properties. What turns out to be true is as long as L is a handle body, then that 4-chain always exists. Otherwise, it's a question whether it exists or not. But if it exists, then you can write this in this one. So this,
This might not be the first time that this idea has come up.
which idea?
That one,
This 4-chain certainly not. It's been there before.
with linking numbers.
Linking number has been there before,
Okay.
but counting by the boundary in the skein has not been there before.
What does it actually mean counting the boundary in this game? The same
The
module?
skein module of the I record the actual boundary.
Excellent.
I mean the point is previously people would remember something like the homology class
Yeah.
of the boundary, and this makes things very difficult. But if you remember the actual boundary, then this solves some problems.
But I think what Vitria Cardino did was very close. I mean, he didn't talk about skiing, but
Yeah, I didn't talk about skein.
right.
Uh,
He had some, he packaged it in a slightly different structure, right?
So-
Some top piece.
So
It's still lookable because
there's a
still lookable.
there's a part of that that's correct, and there's a part of that that's so you will see for the next theorem that it is of crucial importance that we count in this game. So the next theorem says that, I mean just to say, so remember this theorem said that if you want to pick up this whole coefficient ring, then you had better count in this game. So the next theorem says let me give this function a name. I'm going to call it psi xl.
So what's written in the power? Is it KU comma?
It's a linking number between u and L. I haven't told you how to define the linking number. The next theorem says that if I look at the cotangent bundle of S3, and I take the union of S3 and some L disjoint from S3, that is equal to, if the X here is now resolved confold, X resolved confold.
And you're not assuming O is conic.
Nope. I'm assuming L is disjoint from S3. Proof. So the proof is somehow not, there's not much in the proof. You take stretching in a neighborhood of S3. It's worth maybe, so first I'll say the proof. You stretch in the neighborhood of S3, and because S3 has no index zero wave orbits, nothing can actually go inside after you finish.
Psi.
Psi is this function.
So it's just a partition function for the Lorentzian transition
Yeah.
result. I mean,
I don't know if you call it partition.
You mentioned that we just do both streams and there is also.
I just never know if it's called partition function when there's other stuff in the vacuum. You still call it partition function? Anyway, that's what it is.
So, what does it mean S3 union L? So where does L lie?
Not intersecting S3.
He just wants, yeah, he just wants a disjoint locality.
Yeah, disjoint.
For any
Yeah, any Lagrangian. Again, there are some, in defining this linking number, there are some things you have to do, assuming you can do those things. You have to be able to do those things in a way disjoint from the S theory. So, anyway, so the curve you stretch, curves can't go in. And what does that mean? It means, because this is invariant, then as this original thing, which is counting things by their boundary on the S3, is equal to this same thing when you've moved L sort of away. Now the curves don't enter the S3, and then you can just put them in the clone. That's more or less it. I don't want to discuss it in more detail than that because I want to discuss the proof of the first theory.
So just checking if L is on one.
So let me state the third theorem. Theorem. If I take in T star S3, S3 and the conormal to a knot, then first of all, let's discuss where this takes values. So this takes values in, I said, the Skeins module of the Lagrangian. This Lagrangian is disjoint, so it should be tensor product of the Skeins modules. And then there's, and so it's important to know here that the Skeins module of the solid torus, it can be graded by the projection to H1. So like how many times it goes around. So this thing is equal to the class of the knot itself times the class of the tensor, the class of the longitude, at plus higher degree. And the proof of this theorem, as you just compute, is S3, knot. You discover there's a single cylinder, so one cylinder, and it goes from the copy of the knot there to the copy of the knot. So not by accident, this is the same picture as the Uro's knot picture. It's really the same cylinder. So this one is this one, but now we count it by its boundary. And the corollary to this theorem, combine this theorem and that theorem, is that if I take side conifold, this is equal to the Homfley polynomial of K. Plus higher degree. Actually, it's possible to say even what the higher degree terms are. So the Grubov prediction is that they are the colored Homfley polynomials. And one can prove that by reducing to a calculation for the Hopf-link. I'm not going to discuss that today. Are there any questions of the statements of these things? Degree, so the Skeins module of the solid torus, you can ask for each person how many times it goes around. And so I just said that was called degree, and this is the lowest degree term. And in fact, Skeins module of solid torus is known to be isomorphic to ring of symmetric functions. And if you want to tease out the colored Homfley polynomials, you should use that isomorphism. Okay. So let me say some things about the proof of this theorem. First, let me try and explain what it would mean to prove this theorem, and then we can discuss. So let me discuss a bit about perturbations. So for me, I'm going to try and give as content-free discussion of perturbations as possible. So I want to begin this, take some space called maps to XL. And what this is maps from a nodal domain with boundary to XL. And this is some, if you want to do it precisely, it should be some Sobolev space, a way of getting a topology, et cetera, et cetera. And
You mean the domain changes or not?
domain changes, yeah.
There's no solid space.
Okay. Some kind of this Hofer manifold, whatever. So then I would like to take the view that there's some bundle over this, where this is possible Cauchy-Riemann operators. Bundle of Cauchy-Riemann operators. And what it means to give a perturbation is give somehow a section of this. Should give a section. So for each map, you should say, what is the Cauchy-Riemann operator for that? Now, one thing which would give you a section is a choice of a complex structure on X. If you choose complex structure, then you know what Cauchy-Riemann operator should be. And what you are allowed to perturb is that notion. And one feature that an actual complex structure will have is that if you have a map from a nodal curve, then somehow the Cauchy-Riemann operator on that nodal domain is really just built from the Cauchy-Riemann operators in those two pieces. And I want to impose that condition on the perturbations which I study. I think everyone does that. So we ask that the section is compatible with the decomposition. I write this for maps in the nodal domains and break one. So I only consider sections which somehow have this property. So I think that is what everyone does, and now there's something which is not what everyone does. Which is that I ask that that on constant maps, constant means zero symplectic area. On constant maps, this section is triggered. It's now this perturbation is triggered.
So do you mean on irreducible components which are
On irreducible components of which it's constant, I ask that this section comes from an almost complex structure. Section comes from almost complex structure, and in particular, those maps should still be constant.
You divide this space of maps by algorithm or?
Not yet.
Just a map. Map plus complex structure, that's all.
And to be honest, I haven't thought so carefully about this particular question, but if it will make you happy, if I say section is multi-section, then section is
No, I didn't say anything about it, but just what you mean. That's a very good point, actually.
Okay.
basic and constant. So that's easy.
Okay, so I want to explain this word primitive from before. So I said I was going to count primitive maps, and the definition is that a map is primitive. If it collapses no components. So there's no irreducible component on which it is constant. Now, the consequence of this request is that every time you have a primitive map, you're going to be able to add constants to it somehow as much as you want. Okay? But I just don't want to think about them. So let me say what it sort of would mean to prove the theorem that I stated. It's a theorem. What was this time? So it would mean there exists an open set of perturbations, 0, such that, first of all, this primitive maps. And I'm going to give a sufficient list of conditions which, if they were satisfied, they would be proven. Primitive maps are smooth embeddings. Second of all, the smooth embeddings are transversely cut. It's not transversely cut out. And primitive maps. And this property, I would say, not only are they transversely cut out individually, but also in one parameter families over P0. So in one parameter families. It's hard to imagine proving 2 without 3. And then the second, the next piece is that in one parameter families, not staying in C0, in generic ones, the only, so sometimes you're allowed some things which don't satisfy these, and the only things which can happen, so only other behavior, is this, and well, there's one other thing having to do with I still didn't explain to you this linking numbers. There's one other thing having to do with linking numbers. I won't say it. Now, most of this, I think, most of this, I think, is not so bad. But there's one thing hiding in this statement, which I want to bring out. So what does it mean that the only other behavior is like this? Well, what you would hope it means is that you have some particular standard model for this nodal degeneration. And then it looked like the pictures I drew before. And one aspect of having that sort of particular sort of model for this nodal degeneration is that both pieces of that are not collapsed. So something hiding in 4 is the statement that it does not happen in a one-parameter family, that you degenerate in such a way that now one component is mapped to a point. Okay? And it's that statement which makes it meaningful to count only the primitive maps. Of course, you can discuss whether or not that statement is correct. But so the point is, once you believe these facts, I claim that you take 2 perturbations, you count primitive maps, you connect them by one parameter family, and what 4 tells you is that, and what 3 tells you is that nothing changes in P0, and what 4 tells you is that when something changes, it changes by the scaling relations. And we quotiented by those, so it's okay. So let me say one thing about this 4.
So for this primitive, not going to non-primitive thing, would it be equivalent to say that your perturbation scheme has the property that the primitive maps and the non-primitive maps are both open? They disjoint open pieces.
So I don't think that they're disjoint open pieces, and in fact, I think that in 2 parameter families, that degeneration will happen.
Yeah, just in 0, 1 parameter.
Yeah, there's no additional.
Maybe I will point out something. So you consider the case of primitive map,
Yeah.
which may be transversal,
Yeah.
and you build with some constant map,
Yes.
which is not transversal.
Yes.
This configuration varies like infinity,
Yeah.
and by your assumptions, you can never make it transversal.
It's not- But also never countable.
But you have some family of some
Yeah, but-
modular spaces. At the infinity, you don't have a transversality. Suppose modular space has dimension 0. Then there might be the cases that sequence of 0 point
Yeah.
of this open part, which converges to this non-transversal point.
So.
So even if you have a transversality on this big component,
Mhm.
the number of 0 may be infinity. Because it converges to this bad configurations.
I think that was the point of having the primitive and non-primitive open disjoint things. That was why.
No, but this is primitive, but it's a kind of variable with constant number. So by this, so by these assumptions, that kind of some assumptions, this infinity can never be transversal.
Let me make last statement, and then we can have this, have this discussion. So the reason you're supposed to think this 4 is reasonable, it's not a reasonable thing, is that it's a fact. Given, how to say, if you have a degeneration from something with some genus to a map where this piece is contracted, then this piece must have a singular point in its image. In fact, at that boundary.
So what does it mean?
That the derivative of the map vanishes there. So consider, for example, if you have a map from an elliptic curve, and what happens when the elliptic curve tries to bubble to a constant. And the map from the remaining rational curve has a cusp. So
That's true in some cases.
So we write some
argument.
argument.
Need integrability or not.
Yeah, I think so.
For the Lagrangian stations, it's kind of similar to me. So that's the kind of issue. People think about that kind of things, but it's another argument.
Yeah, so let's discuss this. I mean, I think the thing we claim in this paper is that we choose integrable structure near Lagrangian.
Yeah.
So the point is, because of this, then since we ask that the perturbations be compatible with the ones of lower genus in degree, this never happens because we already ruled it. So this kind of degeneration that Kenji was saying, this just never happens. Okay, so I'll stop there. And then
Questions?
Why do they insist on primitive counts?
okay, so let me state a conjecture. In fact, this has to do with this Z. Okay, so you can ask what is the meaning of z equals q to the 1/2 minus q to the negative 1/2. And the meaning is, so Rahul, this is a theorem of Rahul, which says that the total contribution in the closed Gromov equivalent theory of in a fixed degree of an embedded curve in a threefold is q to the 1/2. We shouldn't use q now. I'll first write q to the 1/2 minus q to the negative 1/2 to the minus Euler characteristic of the curve, where q is e to the u, and u is the genus counting fraction. Okay, so the conjecture would be I can drop this requirement to count only primitive contributions at the cost of introducing some Kuranishi structure on these moduli of non-primitive people, and you calculate the obstruction. I mean, Rahul made some obstruction bundle calculation, and the conjecture is that the same obstruction bundle calculation in this open case would give the same answer. And then you get the substitution z equals this thing as usual. The main difficulty in proving such a conjecture is defining the section of that Kuranishi. I think Melissa wrote down this Kuranishi structure, but you have to define a section of it, and you have to analyze the behavior boundary. And so I prefer, or at least didn't know how to do that, so I just did this. Yeah.
So you had, in the past, in the case when K was algebraic,
Yeah.
you had an explicit formula for Hoppley.
That's true.
The general K. So, and you count, it was pure homomorphic count, certain shield, blah, blah. So this is symplectic, and so is it kind of instance of Gromov-Witten equal Donaldson-Thomas?
Yeah. If you had a definition of such a thing, this would be an instance.
Okay, so you say that on the Gromov-Witten side, you should count something not with layers and homology, but with scale modules.
So the counting in the Skein module, so there's like one time when it's not necessary to count in the Skein module, and that's when you're doing something ending on solid torus. And the reason is, for solid torus, the Skein module is isomorphic to symmetric functions. And symmetric functions has a basis of partitions. And partitions is, like, you look at the boundary of your curve and how those boundary components go around. And so the same information in a partition is contained in just how the boundary of the curve mapped. And so historically, when people would do it, when the physicists were writing these predictions, they would count by how that partition of how the boundary of the curve mapped. And for the particular case of solid torus, that's equivalent information to counting in the Skein module. And so that's why the predictions are correct.
And your story is about three-dimensional sphere.
No, three-dimensional any manifold.
No, but it's on the other side. If I start, you had a cotangent
I mean, the cotangent bundle can be cotangent bundle of any manifold. The thing which requires the sphere is conifold transition. In fact, there are other conifold transitions for certain other three manifolds, and you could deal with them. And the difference would be those other three manifolds, they have some index 0 wave orbits. So there's some slightly more complicated analysis and calculation of what happened, and the Skein module would have larger dimension. So there wouldn't be somehow one harmfully polynomial, but several.
But still you will have this, the first or second theorem which relates the count, say, cotangent bundle or whatever.
Yeah, I mean, in these other cases when you have conifold transition, you could prove such a thing.
All right, well, let's thank Vivek again.